Okay, good afternoon, everyone. Today we will continue our topic. In today's lecture, we will study the interference and the standing wave. We will be able to derive the standing wave function from an incident wave or a traveling wave and a reflected wave. In next lecture, we will be studying the resonance. Okay, so to refresh your memories from last lecture, we introduced the traveling wave, or we call it sometimes incident wave. We introduced the function of the incident wave, and we explained all the definitions related to that function, where we said that we have an amplitude that represents the maximum peak and the minimum peak of the wave, the number of the cycles per second, which are the number, how many complete cycles we have per second, or the frequency. The unit of the frequency was hertz. The angular frequency, which is radians per second, equals to 2 pi f. The period, which is the time one complete cycle takes, as a unit of seconds, and also the relationship between the period and the frequency. We said that the frequency is the inverse of the period. And the wavelength, which is the length of one complete cycle in the space domain. And we said that the unit for the lambda was meters. Then we introduced the wave velocity. We said that one wave has a wavelength of lambda during a one period time. So if this wave travels one full wave of lambda in one period time, which is t, then I have the wave velocity would be this lambda divided by the period. Or if I use the relationship between the frequency and the period, which is the inverse of the period, then I can write the wave velocity in terms of the frequency as f lambda. Then we introduced the wave number. We said the wave number is the change of phase and unit length, radians per meter. And we said that the relationship between the wave number and the wavelength is 2 pi divided by meter, by lambda, 2 pi divided by lambda, which is radians per meter. Then we said we can look at the traveling wave or the incident wave based on the way it propagates. And that's defined by the sign between the omega t and the wave number times the axis of propagation. So if this sign is negative, then my wave is traveling in the positive direction. This variable defines what axis is this direction. So if it's negative and this is x, then it is propagating in the positive direction of the x. If this sign is negative, is positive, and this is also x, this means that the wave is traveling in the negative direction on the x-axis. So this sign, positive, negative, defines the positive and negative direction of propagation. And this variable defines in space what axis this wave is propagating along. So when I say omega t minus kx, this means I have a wave that is traveling in the positive direction along the x-axis. When I say omega t plus kx, this means I have a traveling wave that is propagating in the negative direction along the x-axis. So keep an eye on the sign between the omega t and the wave number times the the space variable, this one defines if the wave is traveling in the positive or negative direction. And this space variable defines what axis this wave is propagating along. Now let's look at this example here. If I have those two waves, such that the wave is propagating in this direction to the right. And this is my positive direction of x. This means that the solid line function is the wave happening before the dotted line function. Make sense? If it's propagating in this direction, then the solid line wave is happening before the dotted line wave. So let me call the moment or the time for this solid line as T1, and for this dotted line as T2, such that T2 is greater than T1. So T2 is happening after T1. What are you expecting the position on that spring? So what's happening here, this is a transverse wave, first of all, on a string. And it's traveling to the right direction at this instant and that location. The motion of the piece of the string marked with the dot, I'm calling it A1. Is it going to be moving up or down? If the wave is moving to the right, and this A1, if the wave at that moment T1, then where are you expecting this dot to be on a wave at T2? Up. That's correct. And the way to look at it is this way. Draw a line such that this line is vertical this way. Remember, what did we say about this line? This line in a transverse wave represents the direction of oscillation for the matter. So this piece of the string here on this location, that is A1. So let's assume that this position is A1 on the x-axis. Then this A1 is going to oscillate in this transverse wave. It's going to oscillate up and down. Is that right? Now, in order to know where is that point is heading to, draw this line and look at the wave, the intercept point between the wave and this line, and compare it with the two moments that we are evaluating those waves at. So for me, this is A1. And now this is going to be A2. The intercept point is indeed this dot that is represented by A2. And I can easily see then that this A1 is went up. Now, let me show you this. If I am to look at a different position on the string, if I am to draw this line, now this line, of course, this string is going to oscillate between the maximum and the minimum, right? The maximum and the minimum, the positive peak and the negative peak. So if I am to look now at those points, this point, let me call this one B1. It belongs to the solid line, which is the wave that's happening at T1. What are you expecting this point on the string to move once the wave propagates? Down. Anyone else? Up or down? Down, 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 down. If you look at the intercept point, then this should be B2. In other words, it depends on the location that you are looking at the moments of interest. So for A1, for that position at that moment, when the wave propagates, moving this way, A1 moved to A2. But what happened to B1? B1 moved to B2 down. So one of them went up, the second position went down. So not necessarily that they will go up together. It depends on the location with respect to the wave. Is this understood? Is that clear? Okay. So the answer to A1 is up. But if I ask you about B1, the answer should be down. Okay. Now the wave interference is happening when we have two waves are overlapped. In this case, we will be using the principle of superposition between those two signals, which means that the final function is the summation of those two functions. And that's a principle of superposition. So if we look at this example here, this example says the following, or reads the following: use the principle of superposition to determine the wave that results from the combination of the two waves in the following diagram as they completely overlap. So we're looking here at two waves once they overlap, which means I'm looking at them when they both becomes like this. At that moment, I need to apply the superposition. Which function do you think the correct function would be out of this superposition? A, B, C, D, or E? D, this guy. Do you agree? Well, draw this line and look at every point and its corresponding point and apply the superposition. What you're going to end up with is a function that looks like this. Because at the end, you're adding positive value to a negative value, and since this function, number one, is greater in amplitude than function number two, it will be the dominant, at least, shape, right? Or the dominant result. It will be in the upper half of the y-axis. So the answer is D. Take every point and its corresponding. You're always going to get a value that is positive. So if you look at two sinusoidal functions that are overlapping, which means that they are in phase They have the same frequency. If they have the same frequency, this means that they have the same wavelength. And also, the resultant function has the same wavelength. The frequency is not going to change when you do the superposition. But once they overlap, what's going to happen is if this function is a sine theta and this function is a sine theta, then the outcome would be 2a sine theta, which means a function that has the same wavelength, same frequency, however, the amplitude is doubled. This is if they are in phase. They completely overlap in phase. But what happens if they completely overlap out of phase? Which means you're adding a sine to an inverted sine. What happens? So you're adding here a sine function to an inverted sine. So once they overlap, the result is going to be 0, right? They would cancel each other. So this is what we call the destructive interference, where those waves, they tend to cancel each other, and this one is the constructive interference. When they overlap, they tend to add. So the standing wave at the end is a result of this interference between an incident wave, the wave that we have introduced and talked about in last lecture, which is this wave. Displacement as a function of space and time equals to the magnitude A times sine omega t. So if we assume that this wave is propagating in the positive x direction, then it should be omega t minus kx. So this is the incident wave. Now what's going to happen once this wave is being reflected at the end of the string, due to that string being tied to the wall, for example, the boundary condition or the condition applied by the wall on that string will result into a reflected wave that has an inverted amplitude. Inverse amplitude, which means I have here an inversed sign. That's why I have minus A. Why is this? Because at the end of the string, I have to apply the boundary condition and have a 0 displacement. In order to do this, the amplitude here has to be negative. So the inverted signal has a negative amplitude, minus A. Okay, so we understood why we have a minus here in this reflected wave. What about the positive sign here, the plus sign? Because the reflected wave now has a flipped direction. So if my incident wave was propagating in the positive direction, this reflected wave now is going to propagate in the opposite direction, which is the negative direction in this case. And that's why I have the plus, the positive sign here. X, I am still along the x-axis. So the reflected wave is minus A sine omega t plus kx. So we have the negative sign ahead of the function because of the reflected wave, and to apply the boundary condition right at the end, I have to have this minus. And the plus is due to the direction being flipped from positive toward negative. And x stays the same, which is the axis of propagation. So if I add now, apply the superposition of those two functions, I will get this function. This is the standing wave function. Now, where did this stand? How did we derive this function? By applying the superposition. So if we say that the incident wave, which is a function of space and time, equals to A sine omega t minus kx, traveling in the positive direction of x. Then this wave, when it's reflected, it's going to take this shape. Y reflected equals to minus A sine omega t plus kx reflected and minus x. Now, if I apply the superposition and add those two functions, I get the total function also as a function of space and time that equals to y incident plus y reflected. Where y incident is A sine omega t minus kx minus A sine omega t plus kx. If I take A outside, and this derivation is only to show you how did we get this function, minus sine omega t plus kx. So now I have a sine, a difference of two sines, of two phases. One of them is omega t minus kx, and the second one is omega t plus kx. Now, if I use the following trigonometric identity, that is basically says sine alpha minus sine beta equals to 2 sine the difference divided by 2 cosine the summation divided by 2. I use this trigonometric identity with the understanding that this is alpha and this is beta. I can rewrite now this total equation, which is y function of xt equals to A 2 sine alpha is omega t minus kx minus beta, which is minus omega t minus kx cosine alpha plus beta, which is omega t minus kx plus omega t plus kx. This is divided by 2, divided by 2. Then omega t is going to cancel. Okay, x also is going to cancel, so I have y xt equals to a 2 sine minus 2 kx over 2 cosine 2 omega t over 2. Now 2 is going to cancel, and this minus is going to go outside. So I have here minus 2a sine kx cosine omega t. So this is the standing wave function. And what does this function mean, or how can we interpret this function? This function has doubled the magnitude. The amplitude is doubled. It's a sine function in a space domain that is multiplied by a time-varying cosine function. What does this mean? This means this omega t is going to result into a function that varies between 1 to minus 1, multiplied by a sine function with a double the amplitude, which basically going to result into the peaks changing between maximum and minimum, because it will be oscillating between 1 and minus 1. So at the end, this sine function that has doubled in amplitude, it's going to oscillate up and down due to this cosine omega t. So this cosine omega t at the end is going to vary between 1 to minus 1. And it's a function of time. As long as the time is going, then this function is going to sweep between minus 1 to 1, which basically going to result into the maximum peak and the minimum peak switching positions. Is that clear? We're going to see a demonstration that shows what do I mean by a sine function that is oscillating between maximum and minimum, between positive amplitude and negative amplitude. Any question about how did we derive this standing wave function due to the interference of an incident wave and a reflected wave? Okay. So this wave, as we will see later on, it's not going to move. It's not going to propagate. It's going to oscillate, and it's going to look oscillating in its place. No motion, no propagation. To understand what do I mean by this, let's watch this movie together here that shows us how the standing wave is constructed due to the interference between incident and reflected. Okay, so this is the wave, one incident wave, and this wave will be reflected back. Watch the wave, the incident wave and the reflected wave once it reaches the end. And then if you keep generating those waves, you're going to end up with waves that are incident in red, and you can see the blue ones are being reflected coming back toward you. Now, this black envelope, what you're seeing here, is the standing wave. So this is what I meant by a sine function that's going to be oscillating due to the time-varying cosine function that you're multiplied by this way. So you can see that the positive peaks are switching between the negative peaks. Sometimes the positive peak becomes the negative peak, and the negative peak goes to the positive peak, and this is because of the time-varying cosine function that you're multiplying by that function. So that's how the standing wave is being constructed due to the interference between an incident wave, and a reflected wave. You can try this at home. Bring a string, tight it to the wall, and start moving it up and down from one side. Then you will see a standing wave that being constructed in that string. We're going to talk more in details about some of the important distinguished points along this string, where you have what we call some fixed positions and other positions that are oscillating between maximum and minimum amplitude. So I would like to stop here